Hey, welcome back, Penn, Ohio family. It's Mike O'Dell here again with Charles Dillard from Amphenol Broadband Solutions. Charles, welcome back. Thanks for joining us again.
Yeah. Thanks for the invite, Mike. Glad to be back with you.
Yeah, so the first time we talked, we covered a lot about hardline connectors and how maybe underappreciated they are because of how ubiquitous they are on the network. And we got into the construction of the connector and installation practices. But we really wanted to pick up from there because the part that we didn't get to was really how craftsmanship impacts the performance of the network. So let's start there and talk about how important is craftsmanship in the installation of a connector with additional respect to, we talked about the waterproofing thing, and I think I may have started a fight on our YouTube channel about whether shrink boot is required or not. But in full transparency, I do think it was intentional.
Gotcha.
Uh, yeah. So you mentioned that, and all manufacturers say this too, right? There's so much care and engineering that goes into the construction of your connectors that when properly installed on, you know, pristine cable, that additional weatherproofing is not required. And we've done tons of testing that validate that statement.
Yes.
However, the reality is not every piece of cable is pristine. Not all environmental conditions are the same. And so it's really up to the operator whether they decide that additional weatherproofing is necessary. But
Yes.
yeah,
No, you're
go ahead.
correct. The one thing is that you always want to be more stringent when it comes to whether it's policies, procedures, practices. You don't want to go the other way and be less than what recommendations are. So when a company, have a policy of using heat shrink or, even when placing connectors at the tap, some will, say you have to have, grommets, and then you may have to have some type of lubrication around the threading, et
Yeah.
cetera. It doesn't make things worse for you. So as we do training in person or virtual, one of the things that we always lead with is you may hear something that may be slightly different from what your company is doing. So we
Right.
always refer them to their company's guidelines and policies. So yes.
You heard them, kids. Follow your company's policies and procedure standards. Okay, so we've got hardline connectors everywhere. We alluded to in our last conversation that for every one segment of cable, there's two connectors, right? And when you get to amplifiers and nodes, active devices, there's typically four, five, six different connectors on that. Every passive has at least two, maybe three, sometimes more. So connectors are ubiquitous. And speaking to the craftsmanship thing, right? When you're initially installing a network, there's some post-validation stuff that happens, which is basically, is the network working or not when you're done? And if I can share a story, I was still an installer with TCI cable, and we actually had a microburst storm that knocked down a bunch of cable. So the contractors came out and put a bunch of spans up, but we didn't have enough splicers to activate all of these spans. And I'm like, I'll do it, sure. Um, so I got a box of connectors and some tools that I had never used before, and I went out and I spliced this entire feeder run, right? All the taps, got all the way to termination, and I hooked up my signal level meter, and I had no signal. And I was like, well, did something wrong.
Yes.
So
Only
what?
just one thing wrong, but
So I went back to the beginning, checked all of my connectors again, put them all back together again, got to the end, and it was better, but it was still not good.
okay.
And then eventually I learned what I was doing wrong in that the way it was a three-piece connector, and I was tightening the connector in the wrong sequence. So
Oh,
I
okay.
was intentionally sucking it out. I'd never been taught before. It was just like, here you go, here's a bunch of stuff, go figure it out. So that's what happened is I had to go figure it out. And I learned twice the wrong way to install a hardline connector before I figured out what I thought to be the right way because the outcome was that I had signal at termination at that point.
Got it.
Now, I don't work in that system anymore, and I hate to guess how many maintenance technicians have had to visit those connectors in the last 25 years since I installed them to actually install them the right way.
And you break
So
up. I don't mean to cut you off. Go ahead. Yes.
yeah, so craftsmanship is important and proper installation of hardline connectors does matter, not just for whether it works or not, but
Mhm.
I think we're going to talk some more about some of the future technology considerations and some of the things that we don't think about in the context of what our systems bandwidths are today and our modulation types and all of those things. But they really are ticking time bombs if they're not done immediately or done properly um, from the installation phase. They may not fail right away. Like you'll get to termination and say, okay, yeah, I have good signal now. It's approximately what I would expect to have here. Therefore, I must have done it well, right?
Oh yeah, and then especially when, like you were saying, how many techs came after you to have to troubleshoot. Part of because you know because it may not appear like you were lucky that the first time you got to termination and you didn't have any signal, and then you went back and did some checks and it was better or whatever. But there are often times where you will install a portion of the network and everything is working. But then over time, when moisture gets in, or temperature changes, or vibration because it's near a highway and the connectors are not tight, uh, you know, but the worst types are uh, return issues that may be transient in nature. So it may be here because there's a ham radio user who's using the radio at the time, and there's a leak, and now it's throwing this ingress, into the network.
Yeah,
But then you go out there to troubleshoot, and it may be gone. So again,
sure.
I remember just having to troubleshoot return issues back in the day, and if you were lucky, it was still there when you were out there. And if not, then you had to go through your other troubleshooting steps, like, okay, are there any leaks? Do I need to, OTDR the cable, or sweep, that run, just to make sure. Because as you know, it's one thing to have the proper levels throughout each of the active devices, but your response could not be where it needs to be. When you start talking about peak to valleys and stuff.
Yeah. Yeah, let's talk about that because there's really such a difference between, just having signal level, which again, where we came from in the analog days, level really equated to quality
Yes.
in that one-way plant, right? Because of carrier to noise and second, third order distortions, et cetera. But in today's day and age, it doesn't, right?
No.
We're and especially in two-way plants with the high total composite power energy loads that we're sending through these networks. Now things like structural return loss matter way more than they ever did. And the reality is the connectors that we installed 20, 30 years ago may still be out there and they may be properly installed and weatherproofed, and we haven't touched them in 30 years. But when we change the signals that are flowing through them, stuff's going to happen that we didn't expect. So, in addition to the table stakes, right, which is having good tools, taking good care of your tools, properly coring the cable, properly installing the cable, those are table stakes, right?
Yes. Correct.
And there's different types of tools, and there are certain tools that I consider highly precise tools, right? Whether they're fiber optic tools or things that require very precise tolerances in order to work correctly. And if I could go back to the tool section again for a moment, coring tools are one of those things that I consider to be highly precise tools. we don't think about them like that all the time. They're connected to a drill or you're throwing them in your splicing bucket and, they just get banged around. They seem pretty rugged, and they are for the most part. These are all good coring tools. But man, they're highly precise tools. If they're worn or corroded or start to develop burrs, um, you need to take care of those things and maintain them because it does have an impact on the installation of the connector and then potentially some performance stuff, right?
Oh yeah, yeah, and especially like coring the table. I think before we talked about it's one thing to see like a score on the jacket of the outer conductor, but if it's within where you might not notice it, but then over
Yeah.
time, you get a radial crack or whatever. Those are the things that make that precision tool more important because it's taking care of things that you may not see from the outside, just looking at the cable or whatever as you're prepping it. Also even just and I'm sure we've all done it over at some point, but just making sure that when we're cleaning the semiconductor, make sure we're getting all that residue off, dielectric, just not thinking about going down to the next you know portion of the network and having to do it again or whatever is but when you're looking at the semiconductor cleaner, the actual coring tool itself, I mean it's doing some things that we could take for granted, and it's easy to fix a problem while you're doing it than having to come back, a week later and try to, number one, locate where it's at first, and
Yeah.
then break everything apart, and then hopefully you can see where the problem is. Where, oh wow, the last technician didn't even clean the semiconductor, or there's as they were heat shrinking it, the heat shrink didn't cover everything. If you're adding, heat shrink as a protection, and now water's travel down the cable, et cetera. So even what we're showing on the screen here, everything is important. Even like just cutting, putting that bevel pyramid cut onto the
And the center
semiconductor
conductor. Yeah.
itself and stuff. So over time, you can take it for granted because just like any job, you can start to where you can do things in your sleep. However, you don't want to get to the point to where you're not even physically checking your tools and making sure that they look okay. Same
Yeah.
way like with your safety equipment.
Yeah, and we talked about cleaning the center conductor. These tools, both of these tools have plastic teeth at the end of them so that you don't remove any of the copper from the outside of the center conductor. I
I'm using.
know a lot of us grew up with using a utility knife or a knife, right?
Oh
And
yeah.
scraping that off. And, again, in those days with those signal types and that technology, you might have got away with it without significant impact to the performance of your network. But in today's day and age, you're not. Because that center conductor isn't full aluminum or copper. It's actually a copper clad aluminum, and there's a thin layer of copper on the outside of that. And if you scrape any of that away, we know that the signal, the higher the frequency, the more that tends to be impacted by the quality of that exterior center conductor surface, called the sheath effect or the skin effect. Um, so those are really important. And then you mentioned having that good diamond bevel on the end of the center conductor. I know the Gator tool has that. It's actually a center conductor sharpener, so you get a nice bevel before installation. But all that stuff is crazy important. And then I'm going to pull the pin on the grenade again.
Okay.
When we look at the cross section on your connector, we've got all of these joins, where there's weatherproofing in there. So obviously the O-ring on the 5/8 that connects to the housing of whatever you're connecting the cable to. But then these other junction points also have O-rings for additional waterproofing. Again,
Yes.
kids, follow your company's recommended guidelines and practices. Um, but when we look at the cross section of the connector, we notice a couple of things, right? First of all, that solid brass construction, you can actually see it once you get past the coating of the connector itself, but you can see that brass and the conductivity of brass is just such a great material.
Yes. Very.
So it's very robust. So we can see the mating of the teeth. Unfortunately, we can't really see the helical grip of the pin attachment to the center conductor, but that's happening in there too. So, that's another design feature that's sort of unique to your connector.
Yeah, especially, like I said, occasion where suck out could become an issue if there's something that may not be, the quality isn't there 100%, because, our connector is grabbing it further down onto that center conductor. It will help to minimize. We're not, guaranteeing that you won't ever have suckouts, because you have to do everything else right, like with the craftsmanship, but it will definitely help to minimize it.
Okay, so we've talked about the good. Let's talk about the bad and the ugly. Um, there's there's a lot of opportunity to get this wrong, and you may not notice it right away, but eventually, these things are going to rear their ugly heads, and it's always the most inconvenient times. But there's a lot of opportunities to, improperly install a connector, get it cross-threaded. Look, I get it, guys. We've all done a lot of connectors in a lot of places, in a lot of, uncomfortable positions, whether it's in a pedestal or on a pole, on a ladder, on hooks, in a MDU box or a pit, whatever. It's not always easy.
Yeah.
Sometimes it's hard to get those threads started. You may think you got it. Maybe you're in an underground installation. You got one of them started just right. Everything went swimmingly. And then you go to start the second one. It's just not quite right. You don't want to over bend the cables to get that angle just right in case you kink the cable. And, that's even worse. So, man, it's easy to do.
Oh yeah, even like, back in the day where you would heat up the cable, to, whether you're removing heat shrink, or it would help you to get a connector on, in the wintertime. And same thing with drops, and it's making your life easier at the time, but you're changing the characteristics of that cable when you do that. And like you mentioned, you may get away with it now, but they start to go up to like 1.8, and then eventually 3.0. I'll be probably gone before then. However, it's going to show up, sooner or later. And even just looking at these images, you can kind of see where stuff were either over torqued, with their wrench. And sometimes we feel that, let's give it an extra or two. That way we make sure we don't have any leak or anything. And they're designed with a ours is designed with a positive stop, so you don't really have to just overdo it, especially if you ever had to break them loose for whatever reason. Let's say you're going to update the active or device that it's connected to. And if you can't get them off, now you're going to have to cut the connector off, and now you got to splice in additional or use an extension. And so now you're creating another failure point in the network.
Yeah, I think this is a good place to pause for a couple of public service announcements, Charles.
Okay.
One, I confessed last time to being the 900-pound gorilla that likes to over torque stuff. Don't do that. It has a positive stop. When you hit it, stop.
No. Yes.
The second one is where you mentioned heat. For those of you that in a pinch will heat up like some MC squared cable and use a screwdriver to push the discs because you don't have the right coring tool, don't do that. Use the right coring tool. Like because we all know what happens. It's like, oh, it's in a pinch. I don't have the right coring tool. I got to get this back on. So you do it, you get it on there, you restore service, and then you walk away. It's like, oh, I'll come back and get that later.
Oh yeah.
You're not coming back to get that later.
Oh,
It's
yeah.
going to be there until failure. So don't heat up the cable just to push the connector on. That's bad. Don't do that. And don't over torque your connectors. Hit the
Yes.
positive stop and then take a breath. Okay. So what happens when the connector is either improperly installed or fails because of craftsmanship?
Yeah. So, I know we're talking about hardline connectors, but in the drop connector world, and not really talking about like return, but typically if your drop connector, say at the tap, and I'm just speaking like with forward signal, uh, the worst that could happen is that customer has inadequate signal at the house, and something may not be working, or it may be a grainy look back in the day when it was like analog. Uh, but it would still only affect that customer, that's connected to the other end of that drop. And then when we introduce a two-way system, depending on how severe the connector is on that drop, and if there's any, ingress related to it, you could it could funnel back, into the network or whatever. But with that hardline connector, you know, that impact could affect, you know, 64, 120 something, 200 customers, just on the forward alone. And then so if you have like an active device hooked up to the other end of that cable and it splits off, like you could have an entire neighborhood not working, and that's just on the forward alone.
Yeah.
So I guess the first impact that people need to be mindful of is that uh, you have to start thinking, from like micro and macro, for us looking at the network and the impact that it can have. So now when you start, especially today, where everything is DOCSIS, and I think we're going to talk a little bit later about like future technologies like FDX. I don't want to jump ahead. Well, actually, let me just say it, and then if I do jump ahead a little bit, you can be like, hey, yeah, I think we had a slide on it. But probably one of the biggest thing is that um, if you look over the past couple of years, as we've migrated to like DOCSIS 3.1, and then we'll be getting into DOCSIS 4.0, is that, you know, before DOCSIS 3.1, when we would think about like a QAM channel where it's 6 megahertz wide, when we get into like DOCSIS 3.1, we start introducing like OFDM. So now you have like wider channel blocks.
Yeah.
And so it's one of those things of where the impact nowadays, especially with a connector, before we can get into future stuff like FDX, which is has its own unique issues that can happen if the network is not working correctly. But the thing is that the impact on the network is now greater. With the same poor craftsmanship that we had 10 years ago, so we just have to change your thought as to now, instead of affecting a 6 megahertz space, you could be affecting 96 megahertz and all those subcarriers. And then also the same thing with where we used to have modulation of like 64 QAM and 256. Now it's like
4K.
4096.
Yeah.
So just wear a different hat when you're thinking about what could the impact be with connectors today.
Yeah, this is one I know you and I were both looking for visuals on this, because this is a common trap that I think a lot of technicians are running into today. So the scenario is this: you've been operating a network that has been maybe 750 megahertz for probably close to 20 years now. And, for whatever reason, your limitations were your channel plan itself.
Yeah.
You've only had video carriage signals out to 750 megahertz or so. And it's been fine, right? Typically, there have been sub-split. You're only looking at the return from 5 to 42 megahertz, and your downstream channel plan only goes out to 750 megahertz. Okay, awesome. Well, then you go to, something in DOCSIS 4, whether it's extended spectrum DOCSIS or frequency division diplexed, where you're pushing out to 1.7 gigahertz, or you're doing, a full duplex DOCSIS or FDX that's going out to 1.2 gigahertz. Well, what happens is you start adding energy, like in those OFDM channels that you mentioned. And I know some of those channels are up to 192 megahertz wide. So you go from a 6 megahertz channel to 32 SC qualms in one OFDM channel. Well, you can't add that in your 750 megahertz spectrum because it still contains your linear video or your digital switch video or your video on demand channels or whatever. And oh, by the way, you're adding more upstream bandwidth. So you're pushing your downstream higher in the spectrum while adding additional channels to your service. So now your stop frequency for your active channel load isn't 750 megahertz. It may be out beyond 1 gigahertz somewhere, 1.2, 1.6, whatever. So here's the thing. When we activate spectrum in those channels, because most of us, if you had a 750 megahertz channel plan, you didn't necessarily put sweep points in an active sweep transmitter and sweep out to 1.1 gigahertz, because why would you? There's nothing there. Who cares? So if there was a frequency response problem in that spectrum above 750 megahertz, A, nobody noticed because there was no active energy there, and B, we didn't sweep that high. So as soon as we put spectrum in those channels, now all of a sudden we see frequency response problems and we see, signal quality problems. And we're like, what the heck? What is the problem? We think it's a bad span of cable or a bad amplifier or something. It could be the connector that just has a frequency response above 750 megahertz of something. And that we just never noticed. So
yes.
I mentioned, I think last time we talked is you guys test these connectors all the way out beyond 3 gigahertz for frequency response. The flatness is important. When connectors were made 30 years ago, they weren't sweeping them out to 3 gigahertz. That was lunacy, unless it was like a 50 ohm connector for satellite or something that actually operated in the C-band or up there somewhere. But in the network HFC 75 ohm connectors, there's nothing up there. Why do we care about frequency response above 1 gig?
And even if your test equipment could even sweep out that far, so it just depends on that as well. And because the other thing, and I like where you were going with that is that it wasn't a problem then, so you didn't really worry about it, until you actually needed it. And then the other side of it is that as we start to talk about noise, is that the benefit of going out to 1.8 and introducing DOCSIS 4.0, 3.1 and 4.0 is that we can have higher modulation schemes or profiles, which will increase throughput and all of that. Well, the trade-off to that is it requires higher SNR or better SNR. Mm-hmm. And so the more and more we have issues with connectors, then it will, degrade SNR, which affects, modulation. But I say all that to say, even with the bad side of, what a poor connector can cause on the network, the one great thing about DOCSIS is that it's backwards compatible. So it doesn't mean that it will just stop working. It would just mean that you're not getting 4K modulation. You may be back down to 256 or 1024, unless it's just severely degraded, and then nothing is working. So.
Yeah, in instances like that, like if the PLC pilot on your OFDM channel is wrecked, that device will just stop using the OFDM channel and go into a partially bonded state and just use SC-QAM. So effectively, it's acting like a DOCSIS 3 modem.
Yes.
So, that is a great feature. And you bring up some great points about the way our networks work today is there's a direct correlation between signal quality, modulation order, and then throughput or spectral efficiency. And what all of those have in common is they can all be affected by your frequency response and the performance of the craftsmanship in your node. So you think, it's just a connector. Why do I care? Well, you'll care when you end up with a frequency response problem that results in low MER. So now you've got downgraded modulation profiles, and your gigabit throughput customers aren't getting their downstream speeds. And you're like, what the heck? Well, yeah, it's all about the craftsmanship, stupid. So,
Oh yeah, and I think maybe a future you know training that I would love to, whether it's myself and you or another guest, but to talk about the difference between good signal and a good response, because they are not the same things,
they're
and
not.
it from a tech from an installer perspective, is that it's kind of like you have a drop at a customer house that is bad, so you have low signal, and you put an amplifier on it. Your levels go up, so your levels look good, but you just
Yeah.
amplifying the noise, and which could be the same thing when you talk about what are your levels at the active devices or the tabs, but what's your frequency response, and so when you're sweeping, are you sweeping at 2 dB per division or 5 dB per division, so it's like, are you really close enough to where you can see all the imperfections, or are you like 30,000 foot view of it, so all of that comes into play, and what is that peak to valley, your forward and your return, whatever your company set up, it's very important, especially as you introduce more and more technology and your bandwidth goes out to 1.8 and higher.
Well, it all looks good at 10 dB per division, Charles.
Well, that is true. I love that dB per division.
All right, so this one's a given. I think this one everybody kind of inherently understands from all of the years now that we've been actively working like sub-split
Yes.
return. Noise. I don't, someday I do want to have the argument of the distinction between noise and ingress. But it's for most intents and purposes, we think about noise and ingress the same.
Yes.
Is it something that shouldn't be there? I love Ron Rannick calls it the carrier to junk ratio. So you got your carrier amplitude where it's supposed to be, then you've got to measure the junk. So whether noise or ingress, connectors have such a big part in this. And I don't want to overstate it or understate it because we talk about shielding and also not enough. But in the context of shielding effectiveness is contingent on both the connector and the cable being properly paired together. Individually, as individual components, they have unique and distinct shielding effectiveness values. But what's important is when you put them together in totality, your network, the old saying, a chain is only as strong as its weakest link, is the same in cable, particularly when we're talking about noise or ingress from over the air energy sources, who, by the way, are licensed to be there. You
Yep.
mentioned a ham before, but there's CB, there's AM radio, FM, well, AM's below us, but FM radio, UHF, VHF, LTE, like all of that stuff. Those are licensed spectrum holders. And through the concept of frequency reuse, we're both allowed to use the same frequency. And the only thing standing between the over-the-air energy from those licensed spectrum holders and our system as a closed system is the shielding effectiveness of the conductors themselves. And so when you improperly install a connector or improperly core a piece of cable, or the cable shielding itself is damaged by squirrels or radio cracks or whatever, the shielding of the entire network is diminished. And so is the impedance. So
Yeah.
it's not about one or the other. It's about both and, maintaining the physical structure and electrical integrity of the conductors themselves. So this is a big one.
Yeah, and when you think about leakage, um, if our industry was like the plumbing industry, you would see the effect of leakage in the plumbing industry
Yeah.
like really quick.
Our water bill would be crazy high.
Yes. So in order for us to coexist, like you were saying, with other entities that are allowed to share the spectrum, we have to make sure we maintain that closed network. Because if not, we're going to have flooding, and then now the people that does the carpet or the flooring, they're mad at you because the plumbing was leaking. Same thing with
Yeah.
our industry as well. So
Yeah, for sure. So, all right, let's talk about future stuff. For me, this one hits home for me, obviously, because I work for Comcast and
oh yeah,
as far as I know, we're the only ones doing full duplex DOCSIS, and it is crazy exciting, but it's also terrifying to think about. It's one of those moments where if you are not a mathematician, you you kind of grow up thinking, wait, you can't send upstream and downstream signals on the same frequency at the same time with no diplex filter. It just shouldn't be possible.
it shouldn't be.
But
Yes.
it is. And so it's crazy to think about. But your third bullet point here is the one that's really important. The way that it works is by echo cancellation, right? So once you get your head around the fact that you can have two signals being transmitted in opposing directions at the same time, at the same frequency, and they won't interfere with each other is staggering. However, the important bit is there's with any signal, we'll call it the incident signal, there is typically an echo or a reflection, right, back in the direction of travel of the incident signal. And this exists today in diplexed networks, right? That's your return loss value. So it's usually a very small amount of the incident signal that gets reflected back in the upstream direction or in the northbound direction. And so when you have a bad mismatch or a significant reflection, now more of the incident signal is reflected back upstream. And that's where we start to run into trouble, right? Because when the incident upstream signal is trying to travel through that plant, it may not have the same reflection coming from the opposite direction. However, now it's additive.
Yes.
The receive amplifier now has to see the additional reflection in addition to the upstream incident signal. And it can't always cancel that echo from the incident reflection in order to hear and receive the upstream incident signal. So it's really complicated. And
And the fact that FDX, for it to work, relies heavily on the whole concept of echo cancelers. And, where, like you were saying, it'll send a test signal out to kind of measure what the echo reflection should be under normal situation. So that way, when you have that upstream and downstream, working together, then it will just come up with a code, if you will, or a mathematical filter to filter out what it should have been based on that test echo. And but when you have a connector that's bad, that is introducing this additional reflection, and it could be intermittent, then it creates a blind spot, if you will, for the echo cancelers, and which could be the difference between FDX working the way it should or not. I commend Comcast for taking the early stages on this new technology and working out some of the bugs and coming up with some of the best practices with it. But eventually, it all comes down to basic stuff.
yeah.
Do you have bad connectors and craftsmanship and all that kind of stuff?
The other thing that's unique about this is we've been conditioned in systems that have diplex filters that there's isolation or separation between the upstream and the downstream, and never the twain shall meet. With FDX, there's no diplex filter. So if you have ingress in the FDX band, which goes from about 108 megahertz to 684 megahertz, if there's ingress in there, it's going to affect the upstream and the downstream. That's where it gets really crazy. And again, there's a lot to get your head around with FDX that's different than
Yeah, and I
everything
think the
else.
last couple of slides, I think we just have a couple of slides left, but it speaks to that as well. It's like where it used to just affect the return, in your legacy network or, your traditional HFC. Now it's affecting everything, so.
Yeah, and the added benefit of isolation at the amplifiers, right? Not just the devices themselves, because the amplifiers had isolation and diplex filters in them also. So typically, if you had, ingress in the VHF band or whatever, it wouldn't go upstream through the amplifier because it would run into the diplex filter and not move further north than the amplifier itself. With FDX, there's no diplex there to isolate any of that noise. If it gets into the network, it's going to go both directions,
Oh, yes.
downstream and upstream, because there's not going to be a diplex filter anywhere to stop it. And so that's terrifying.
It is. Good luck with that.
Thank you. Once we figure it out, we'll let you know. But
yeah, they give us all the clip notes and everything. So,
well, the folks at Broadcom are doing some really good work with their DOCSIS 4, SOCs and chipsets.
okay.
So the cool part about this, not to get too far down a rabbit hole, but at the point where we do have ingress in a system, we'll actually be able to look at the spectrum on the port, like the southbound port of one amplifier and the northbound port of the next amplifier, and say, okay, we see it in both of these places, therefore it must be in here.
Gotcha.
So,
yeah. And then the information we're getting from modems nowadays, where when we first rolled out modems, we just used it just as a, an endpoint, for the data. But now it's like, yeah, let's leverage the modem, so it's pretty cool what these smart people have come up with.
Yeah, and the cool part about that is the technology that's in the modems that allows us to use those P&M tools to look like RxMER now is in the amplifiers.
Yeah,
so we can get that. Yeah, we can get the same thing out of the amp and say, oh yeah, this is in the plant. This is not just in the house. Because the hard part, it was always before, all of that noise, particularly in the return, whether it's subsplit, mid-split, or high split, would all aggregate back to, a single point because of the funnel effect. And so whatever noise got in there was all kind of mashed together. And you couldn't really localize it without, visiting the network and, plugging into your return test points and divide and conquer, yeah, all that. But with these amplifiers now and things like UDA, the upstream data analyzer in the Broadcom chipsets, like you can see it right at the device if it's in the house, but you'll also be able to see it at the amplifier. And you'll be able to look at those two things and say, oh yeah, these match. The noise I'm seeing in my house is the same thing that I'm seeing in my amplifier. Therefore, it might be getting in the plant, depending on, localization if you're seeing it on other devices. So the future is very interesting, complicated, but that's what we're here for, right? Is to help make sense of things. But the other thing that you mentioned in here is this CBRS and some of that unlicensed spectrum, and like I say this all the time. If you've never gone outside with a good spectrum analyzer and a good antenna and looked around at what's bouncing around in the air, you should, because it's a lot. We're in a really hostile over the air environment. There's a lot of energy out there.
Oh yes, yeah.
So if you do that, and you probably want to go hide in your basement with a tinfoil hat on, because it may surprise you how much is actually bouncing around in the air all the time. Yeah, so this is the other part, the frequency response and the impact on shared spectrum. Is one that we've already talked about a little bit and alluded to, but not specifically in that FDX band.
Yeah.
But frequency response problems before were either upstream or downstream, but now they could be upstream and downstream. So
which is basically to a customer, it's an outage. I mean,
Yeah.
if their internet is not working, but then your television stuff is not working, it's out to them, whether they're signal
Right.
dealer or not, so.
Yeah, and when we talk about FDX in particular, in its furthest iterations, all the way out to 1.2, and with full bidirectional signaling in this 108 to 684 megahertz, in that universe, there is no more linear video QAM. So it's all IP video over DOCSIS, right? So
Oh yeah.
now your data and video are connected in a way that, we have customers today that are IP video, and that's fine. But the linear video stuff is still there if they have a linear video box. But in a future fully mature FDX world, there is no more linear video. It's all data, which is good and bad. Because when you lose or have some packet loss in your DOCSIS data channels, now it directly reflects on your video also. So it's
The good thing about, being IP based, you introduce, with layer 3 virtualization, so the ability to move information around virtually. It introduces some cool things that companies can, leverage. That instead of everything being at the physical layer, back in the day with networking, you would run your Cat5 or whatever, and everything would be, hooked to the same, hub or switch. But as you start getting to like, layer 2 and layer 3, you can have devices hooked together on the same network, and you can isolate them, whether it's with VLANs, et cetera, kind of where we're going, on the cable network, with everything being more logical than physical. So, which is its own set of problems. But
I thought we were trying to simplify this instead of
oh
making
yeah,
it.
my bad. Oh yeah, my bad.
Listen, we don't want to scare people away from the telecommunications industry with all of the complexity that's in it. Because we alluded to this one earlier, the higher order modulation in OFDM and OFDMA signals does have a requirement for higher MER in order to operate. Now, the good part is it is dynamic. So if an impairment happens in your MER degrades, the channel can adapt to it if you have a profile management application running. So that's good. But it also kind of adds complexity to the troubleshooting, and I'm seeing this in our technicians now, because we do have a lot of OFDM signals out there. We're running, multi-gig symmetrical services over coax with FDX. But when you look at your frequency response, even if your frequency response is good, you may have ingress under those channels because of poor shielding integrity, right? So your frequency response looks good. And if you're measuring power, your power is going to be what it's supposed to be, right? But when you look at your individual RX MER or receive MER at the receivers and the customer premise equipment, you'll see that there are sections of subcarriers that the MER is just really poor. Now your profile management applications can say, okay, for those channels or those mini slots, we'll use a lower profile, and maybe it's 512 instead of 4K or whatever. That'd be really bad. But
Yeah.
it's dynamic. So the important part to know about that is that that's intentional to result in better reliability, because the customers may never feel that if you have capacity overhead to be able to reduce your throughput and still deliver all the data to your customers as needed. But the bad news is it may hide some of these problems because your customers aren't calling. You don't have any TCs. If you look at the spectrum in the Y and the X and the Y axis for amplitude and frequency, it may look fine. But the reality is it's severely degraded under the channel because your signal quality and your shielding integrity is bad, even if your customers aren't calling. So that's what makes it a little trickier in some of these newer technologies.
Yeah. And then, just, I guess, to make a closing point for me, what you said was, like, normally techs get focused on, like, okay, what's my, my low frequency, low channel signal, and what's my high, and I look and I don't have packet loss, so everything is good. But now you have to look at all of the tools that like you mentioned, looking at your MER, return MER, and your just stuff that you would normally look at before that could indicate that there's an issue. The old days, different impairments had a signature. When we're talking about like CPD, you have that signature that you would see every 6 megahertz and et cetera. Now you may have to look at a combination of things to see that, oh yeah, there's a problem. And so it just makes it a little bit more complex.
So it's not all gloom and doom.
No.
And I think we say all that to say this as we land the plane here, Charles. Today's networks are more complex, intentionally so, because that's what our customers require, and the advent of DOCSIS technology and how it's evolved. However, coaxial cable is a really robust medium when properly installed and cared for. And as part of that is the connectors themselves. We don't think about how important it is every time that we interact and change a connector. It's just, again, a ubiquitous component. But, the reality is there's a lot riding on getting that right the first time. And part of getting it right the first time is knowing your connector, knowing how it's made, how it's intended to be installed, and what the features and benefits of that are. And then just taking care in your craftsmanship, which also means your tools, your highly precise tools like your coring tool and your center conductor cleaner and all that. And then just taking the time to get it right the first time. And if you do that, then you don't have to worry about any of the really terrifying things that we've talked about, because it'll just work. And that's kind of the beauty of it. But there are times where things are going to happen and it's going to go wrong, and you're going to have to really parse through all of the symptoms that could possibly happen depending on your system architecture and your technology to determine what the underlying cause is. And in most cases, it's physical integrity stuff like cables and connectors, right? So we try to make it sound complicated, but at the end of the day, it's really not.
Yeah. And then, for me, the last thing about craftsmanship is, we talked about the tool part and understanding how connectors are designed, but with any field, profession, it all starts with pride in your work. And, so if you have, the pride to want to do things the right way, then I think the other stuff will take care of itself. You will learn how to properly do it, how to properly, make sure your tools are okay, et cetera. But, just having pride in your workmanship, your craftsmanship, and it'll take you a long way in our industry.
Agreed. So the other part of that, I'll flip over and throw you a meatball and say training is also really important. Going back to the brand new installer that had never been trained to install hardline connectors and how easy it is to get it wrong. If somebody wanted to reach out, and I know Amphenol, these connectors, your new connectors are available all over the place. If somebody wanted to reach out to you and say, hey, Charles, could you come to our system and do a training? How would they go about that?
Yeah, so we can be reached at training.amphenolbroadband.com. Also, we're on YouTube. We have a YouTube channel, Amphenol Broadband Solutions. You can comment on some of the videos. You can get in touch with Mike. Mike has all my information. I can be reached at cdillard@abs-go.com. And that's cdillard@abs-go.com. Shoot me an email. We can do in-person, virtual, send you links to video. We love to get out in front of people, the future of our industry. So.
Awesome. Well, thanks, Charles. It's been a great couple of sessions. Really, this is one that I'm passionate about because they are so important. There are no unimportant connectors in today's networks. So understanding them, understanding what can go wrong, how to do it right, how they're made, has been very informative. So thank you for taking time and for partnering with the Penn Ohio chapter on this connector training. So
I appreciate the invite, Mike. See you next time.
All right. We'll see you next time. All right, kids, that's all for today. Until next time we talk, stay safe out there on purpose.